Assalamualaikum and hi everyone. So today I'll be explaining about the heavy metals analyzed in milk using ICP-OES. So in this video, I'll be explaining about the importance of analyzing the analytes from the sample, why the spectroscopic method is chosen, and the application of spectral data in qualitative and quantitative. Analyzing analyte from samples is essential to determine the presence, concentrations, and potential impact of specific substances within a matrix. The importance of analyzing heavy metals in milks, especially due to the fact that milks is widely consumed, especially by infants and young children who are more prone to metal toxicity. The ICP-OES is used to determine the various heavy metals including lead, cadmium, arsenic, aluminium in their trace amounts, making it possible to determine them accurately even in complicated samples like milk. It is very important to analyze this analyte in order to make sure that they do not surpass maximum permissible levels that are provided by international regulator bodies like WHO and Codex Alimentarius. Contamination of milks by heavy metals can be occur by means of contaminated animal feed, water, environmental pollutions, or even equipment used in the process. A long period of exposure by frequent consumptions can lead to severe health consequences such as nerve damage, kidney damage, and even the developmental disabilities. Thus, the method of ICP-OES analysis of heavy metals in milk are very crucial in monitoring food safety, preventing illness in people, and ensuring compliance with regulation and risk assessments as it ensures quality information on the level of contaminations and the possible dietary exposure. How does ICP-OES work? It works by heating and ionizing atoms in a super hot plasma of argon, which emit light of a wavelength specific to each element, which is then separated and measured by a spectrometer to identify and measure the elements in the sample, which are then used to determine the elemental compositions of the sample. It is an effective method of trace element analysis which reduces liquid samples into fine aerosols and then excite atoms which emit glowing just like a neon light. And this is the explanation of why spectroscopic method is chosen compared with the other methods. The spectroscopic technique commonly used for the analysis of heavy metal analytes in milks is the inductively coupled plasma optical emission spectrometry, which is ICP-OES. This technique is preferred because of its high sensitivity, its ability to measure multiple elements at the same time, and its capability to handle complex food metrics such as milk. Milks contain protein, fats, and carbohydrate, which can cause interference during analysis. However, ICP-OES overcome this matrix effect by using extremely high plasma temperature to effectively atomize and excite element present in the samples, allowing accurate detections of heavy metals. When compared to atomic absorption spectroscopy or AAS, ICP-OES offers a significant advantage. AAS typically measure only one element at a time and is usually less efficient. In contrast, ICP-OES allows the simultaneous determination of severe heavy metals. Although ICP-MS provides even a lower detection limit and is capable of detecting toxic metals at a very low concentration, it is more expensive and complex to operate. Classical non-spectroscopic techniques such as titration, electrochemicals, and chromatographic method are generally unsuitable for trace metal analysis in milk due to low sensitivity, lengthy sample preparations, and poor selectivity for inorganic metals. Therefore, ICP-OES is widely used in milk analysis because it provides accurate, reproducible, and cost-efficient results while complying with international food safety standards and regulations.
Hi, I'm Miza Raihana, and now I'm going to explain some information obtained from the spectra measured based on an article titled Determination of the Level of Heavy Metals in Cow's Milk collected from Butagira and Miskan districts. This article uses ICP-OES as the spectroscopic method and was published in 2021. So basically, from a spectrum, we can identify the analyte, which is the qualitative information, where each element produces signals at characteristic wavelengths. Next, we can determine the concentration of the analyte, which is the quantitative information. The intensity of the spectral signal is proportional to the amount of analyte present. The higher the emission intensity, the higher the metal concentration in milk. The spectrum also shows the sensitivity and detection capability, which includes the signal-to-noise ratio and detection limits. This way, we can know if the trace level detection is reliable. Interference and matrix effects can also be seen by extra or overlapping peaks, which may indicate spectral interferences, contamination, and matrix effects from the sample. And finally, a spectrum shows the quality of a measurement from the peak shape, whether it is sharp or broad, from the baseline stability and the noise level. This indicates how reliable the measurement is. So how can this information used to achieve qualitative and quantitative analysis? Firstly, qualitative analysis emphasizes on what is present. The measured spectrum is compared with the reference spectra and no calibration curve is needed for this. From the article, we can see that, for example, lead emits at 220.305 nm, while cadmium emits at 214.439 nm. So if a peak appears at 220.305, we can say that lead is present. Secondly, quantitative analysis focuses on how much is present in the sample. The signal intensity is proportional to the concentration. The sample's intensity is interpolated from the calibration curve to find concentration. I have a few comments regarding the data obtained from the article. Firstly, the data show good analytical reliability due to high recovery values range from 95.6 to 99.4%, strong linearity with R2 value of 0.994 and low detection limits around 0.001 mgl. So the result is considered trustworthy and not due to any errors. Secondly, there is a wide variation in metal concentrations among samples, especially for lead ranges to 12.3 ppm and zinc ranges to 8.2 ppm, which suggests non-uniform environmental exposure. Thirdly, some metals exceeded permissible limits in large percentage of sample. For example, lead around 82%, manganese around 65%, and cadmium around 12%. This might lead to chronic exposure risk. And finally, the article claimed that nickel was not detected in any sample. This may be due to low environmental exposure or insufficient sensitivity of ICP-OES for ultra-trace nickel. Since Aisha already shared the advantages of ICP-OES, let's move on to the limitations of the analysis and its improvements. The first one is the spectral interferences, where overlapping peaks and background emission occurred. This can be improved by applying background correction technique or using standard addition method when overlap is unavoidable. The second one is the metric effects, where sample components suppress or enhance signals. It can be improved by proper sample digestion, such as microwave digestion. The third one is the poor sensitivity of certain elements, such as nickel, in the study, so we can switch to a more sensitive technique such as ICP-MS to detect nickel. And the limitation of Beer-Lambert law deviation, which resulted in a non-linear response at high concentrations. This can be improved by using monochromatic radiation. This study also addressed the accuracy, where it was evaluated using spike recovery experiments. The recovery ranged from 95.6% to 99.4% for all metals, which indicates high analytical accuracy. Next is precision. It was evaluated using triplicate measurements and intraday and interday analysis. Low RSD values were reported in the article, which shows good repeatability and reproducibility. The sensitivity was assessed through strong linear calibration curves and high correlation efficient, where the R2 values are above 0.994, which means it is sensitive enough to detect metals at very low concentrations. Detection limit LOD and quantification limit LOQ were calculated using blank measurements and standard deviation of blanks. Detection limits can be seen around 0.001 mgl. ICP-OES has a low detection limit suitable for trace metal analysis. Selectivity was addressed from the use of element-specific wavelengths for each metal. Separate techniques is used, for example, ICP-OES for trace or toxic metals and NPAES for major minerals such as calcium, sodium, potassium, and magnesium. In terms of robustness, same digestion and analytical procedure apply to all of the samples. The method is robust as small variation in sample type and analysis condition did not significantly affect results. Here are some of my opinion regarding this study. Firstly, I think the study underestimated the chronic exposure risk. Even if the EDI values below the RDL limits, but chronic low dose exposure to heavy metals still pose health risks. Therefore, it underestimated the long-term health effects. The study also claimed that there was no nickel present in milk. Nickel was not detected due to detection limits of ICP-OES, so ICP-MS should be used instead to trace nickel. Not detected doesn't mean that it's not present. So that concludes our presentation. Thank you.